This is a video for OCR Pure Core Mathematics. Complex numbers 4, De Moivre's theorem. 4.1, De Moivre's theorem. If we have two complex numbers in mod argument form, we can use the fact that the product of the two complex numbers will have a modulus formed by just multiplying the moduli of each individual complex number, and the argument of the product is formed by adding the arguments of the two complex numbers. And you have seen this in a previous sequence of videos. This allows us to quickly multiply complex numbers. So there's our reminder of the theory. So what happens if we have a complex number like this? Z is equal to r times cos theta plus I sine theta. So what we're saying is that the modulus of z is equal to r, and the argument of z is equal to theta. Well, if I square it, that means I'm multiplying r cos theta plus I sine theta by itself. So I should get a modulus of r squared and an argument of theta plus theta, which is 2 theta. For z cubed, I'm going to get z squared times this. So I'm going to get r cubed and 3 theta. And for z to the 4, I'm going to get r to the 4 and 4 theta. And in general, we say then that z to the n is equal to r to the n cos n theta plus I sine n theta. These are multiple angles. Okay, let's have a look at z to the n geometrically. To do this, we're going to look at a dynamic plot of z to the n. On this dynamic plot, I'm going to be able to alter the modulus of z, the argument of z, and the maximum power. So there's my original number, and then these are the powers squared, cubed, power 4, power 5, and power 6 for this particular plot. Okay, so here's that dynamic plot. Notice that each power is getting smaller. In fact, what we've got is we've got powers of 0.8 for the modulus of each successive result, so it's spiraling inwards. And it's going round by theta every time. So this powering is effectively an enlargement with, in this case, scale factor 0.8 every time, and a rotation of 0.79 radians, which is pi by 4. I'm going up to a maximum power of 6. Watch what happens as we increase that maximum power then. 7, 8, 9, and you'll see that it continues to go round, spiraling in towards the center. What happens if I increase the modulus? Well, as I increase the modulus, the spiral gets shallower until, when I get to 1, it obviously tracks around a circle, and you can see what happens as I up the power. It continues to track round and round a circle because the modulus will always be 1. What happens if I change the argument, the initial argument? Well, in which case the rotation will either get smaller each time or larger each time. If the modulus is greater than 1, then the powers will spiral outwards rather than inwards. So as we've just seen on the dynamic plot, if we consider the case where r equals 1, then cos theta plus I sine theta to the power n becomes cos n theta plus I sine n theta. The modulus starts out at 1 and therefore remains as 1. We're going to use this result in quite a few ways, but not least to look at coses and sines of multiple angles. The proof of this result, known as De Moivre's theorem, is in three parts: n is greater than 0, n equals 0, and n is less than 0. The proof is beyond the scope of this video, but you ought to look at your textbook for a detailed proof. The next video in this sequence is 4.2, Powers of Complex Numbers.